Hello everyone, I hope you're doing well. So in this video, we're going to discuss the solutions for Codeforces round 823, which was rated for Division 2, and we're going to discuss problem A and C. So the first question is A, planets, and this question says that we have a machine and we have to destroy some planets. So we can use the first machine, which in one operation can destroy any planet with a cost of 1, and the second machine can destroy all planets in a single orbit with a cost of c, right? And here we have been given 10 n number of planets and the orbit in which it is present. For example, this particular planet is present in second orbit, this is present in first orbit, and this is present in fourth orbit. So here we have been given an input and we have also been given the value of c, right? So it is a pretty straightforward question. For example, if there are some orbits, if this is some orbit, there are planets 1, 2 and 3. If this is some orbit, there are planets 4, 5, 6 and 7. So obviously if we use the first machine, then to destroy each planet we have to give 1 coin. So here it will be 3 coins and here it will be 4 coins. But we have also the second machine which can destroy all the planets in this particular orbit in c coins. So we can just take the minimum of both of them and we can do this for each of the orbits, right? So for each of the orbits we can take the minimum of the number of planets present in it and the value of c, which is used to destroy all the planets in that particular orbit. So this is what I have exactly done in the code. I've taken two integers n and c and I create a map which will store the number of planets in the ith orbit, and then I traverse through the vector, traverse through the input, and I take an input a as a, right? And I increment the frequency of a in the map. Now I initialize my cost with 0 and I traverse the map, and for each value or for each orbit I set the result as minimum of I dot second, which is the number of planets, and c, and I added this particular element to the cost and I just put the final cost. So this would be my answer for the first question. Now moving on to the second question, which is minimum notation. Now this particular question says that we have been given a string s which has digits from 0 to 9, right? So in word operation what we can do is select any digit in the whole string and we can delete it, and we have to insert a new digit which is minimum of t plus 1 and 9. So we have to essentially insert d plus 1, and if t plus 1 is greater than 9 we can just insert 9. So we can insert this new digit at any position in the whole string. So we can insert it at the beginning, at the end, or in between any of the two adjacent digits. So we can actually insert it anywhere, right? So now we have to find the lexicographically smallest string that we can form using these operations, right? So this is our question. Now this question can be answered greedily, but for that let me show you an example first. So let us take this test case, right? So if we traverse from this particular position, from the last position, right, we can keep count of what is the minimum element present till here, right? For example, if in this case 1 is the minimum element, here 1 is the minimum element, 1 1. Actually for this particular test case all of the indexes will have 1, right? So for all the indexes we can calculate the suffix, minimum suffix. For example, if I'm talking about particular suffix, I have to calculate the minimum element present in here from this particular index to nth index, right? Then I have to set count of this particular suffix, minimum element present till here, and then I can keep record of all the suffixes in this particular order. Now what I have to do is, if the current element, if s of I is equals to the minimum suffix, the minimum element in the suffix from position I, if these both are same, then it means the element in the ith position is already at its correct position. What it means is, if I, for example, let me consider another case. Let me take 1 and 3 here, right? So the minimum till here is 3 and the minimum till here is 1, right? So this is the minimum suffix array. Now if when I say that these two elements are equal, right? If these two elements are equal, that means it is already the smallest element that can be present in front of any other element present after it, right? It is already the smallest element and it will already form the lexicographically smallest answer. So I don't need to change this particular element when the value of s of I is equals to the suffix array at the ith position. If these two values are equal, then I don't need to change them. Similarly, we can take another example. Let me take 9, 8, 7, 6. Right. So minimum till here is like this. So these two are same. So I don't have to change this particular element's position. These two are same. I don't have to change this particular element's position. However, if it was the opposite, now minimum till here is 6, minimum till here is 6, minimum till here is 6, minimum till here is 6. So for every position, you can see that these two are different. So I can change the position of this particular element in such a way that the new resulting string would be lexicographically small. But there is one more thing, that when I change its position, I need to increment this by 1. So it would be 9 plus 1 and I have to take the minimum of 9 plus 1 and 9. So it would be 9, right? After I do this particular operation, I can actually insert it at any position, right? I can insert it anywhere in my final answer. So I would definitely would like to insert this particular element at the last because it is the greatest possible, right? So you just have to do this for all the elements greedily and you will form the answer. So what we'll have to do at the end, we will calculate a suffix minimum array, right? After we have calculated this, what we can do is, for all position where s of I, for all positions where s of I is equals to the ith element in the suffix minimum array, then we don't have to do anything for it and we can create a result vector which will store the frequency of all the elements like 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. So this will be the result vector which will store the frequency of all the digits, right? So we can just increment plus plus res of s of I. So this means that we have to include this particular element in our answer. And if these two values are not equal, if s of I is not equal to the ith element in the suffix minimum vector, then what we have to do is we have to increment s of I by 1 and take minimum of that incremented value and 9. So whatever I get C, I have to increment that value in my result vector, right? Like this. So at the end, what I can do is I can just traverse from all the values from 0 to 9. And what I'll just print the number of elements present at that index. For example, if at index 3 it was 5 elements, I'll print 3 5 times. So why am I doing this? Because as I've already told you, when I increment this particular value, right here, so I can increase it, I can place it anywhere in my string. So I would definitely place it at the end, right here at the last position, and this will follow for all the elements present in the string, right? And those elements which I did not change when s of I is equals to the ith element in the suffix minimum vector, these elements would already be present in an ascending order. So I do not need to change their location at all. And for those elements, for those I have to change the location, I can just sort them and have them in my result. So let me show you the code and it will be more clear. So what I do is I just initialize a pre-computed vector, which is the suffix vector, right? And I take the n is equals to size of s. Now what I do is I just travel a reverse loop from n minus 2 to minus 1, and what I do is I just set pre of I is equals to pre of I plus 1, and I calculate the current value of s of I in integer. Now I set pre of I is equals to minimum of pre of I comma c. So it will be the minimum value of both of those. So this way I can calculate the minimum suffix vector. Now what I have to do is I have to create a result vector, and there might be one more thing why I have taken this particular value as the same, right? Because in the suffix, what I'll do is if it is for example 789, I always take the value 9 here because it doesn't matter even if I don't change its position. For example, there are let's say 6, 5. Let me take some regular numbers here, right? Like this. So I change the position of these two elements. Even if I don't change the position of this particular element, if I have 3 elements, I just fix one of them and I can change the position of 2 of them. Then I can still form all the permutations of numbers which I can form with these 3 numbers. Right. So even if I fix the position of this particular number, I can still form all the answers by changing the position of these 2 numbers. Right. So even if I don't change this and I don't increment, even if I don't change its position, then I would still get my answer. So that's why I have taken 3 of n minus 1 is equals to the value of the digit at the last position. Now I traverse from 0 to n minus 1, right? And what I do is I just check if c is the current value of s of I in integer is equals to p of I. Then I increment the result at index c. That means the integer c is present one more time in my answer. Otherwise, what I do is I take the minimum of 9 and c plus 1 and I increment it in my result, and then I traverse from 0 to 10. And for example, if the ith element is present 3 times, I just print it. So this is a while loop for that. And after printing all the values, this would be my final answer. So this was the solution for problem C. I hope you guys were able to understand the solution for this video. So till the next video drops, keep coding, stay safe, bye bye.